Hey everyone, welcome back to my channel. Today we are diving into variational autoencoders and exploring how we can move from data compression to data generation. Let's firstly divide the deep learning universe into two big families. On the left-hand side, we have discriminative models. They like the judges. They focus on learning the probability of a label given input data. In other words, given an image, you try to figure out is it a cat or dog. So it's a kind of mapping input data to the labels. It's like judging or classification. So in practice, we have face ID, span filters, and vision transformers. For the right-hand side, we have generative models. They are more like the creators. Instead of figuring out what is this, they try to learn the distribution of the data itself, so they can generate the new things like the data. Think of it as joining a new cat that never existed before. The example could be VAE, GANs, large language models like GPT. Next, let's talk about some applications of VAE. The first big application is generation. We start from the noise and generate realistic data, like generating images of faces that never appeared before. The second application is restoration. Literally, it's fixing broken data, including things like denoising, inputting, and doing super resolution to enhance the data, the image quality. The last one is representation. VAE learn the meaningful latent space, which is helpful with compressing data, visualizing it, and understanding the rule behind the data. So in short, VAE doesn't just copy data, it understands the underlying rule behind the data. Now here's the motivation. Why isn't the standard autoencoder AE great for generation? A vanilla AE maps an input through the encoder into a single fixed point in latent space. That's awesome for compression. You store the point and decode it back. But for generation, there's a big problem. The latent space can contain lots of regions that were never seen during training, basically holes. If you randomly pick a point there and decode it, the output can look totally weird. A VAE changes the game. The encoder doesn't output a point, it outputs a distribution, usually the parameters of a Gaussian like mean and variance. This encourages the latent space to become continuous and smooth. So nearby latent codes decode to similar value samples. One sentence takeaway: AEs compress well but generate poorly. VAEs use distribution to make latent space smooth, continuous, and sampleable. Now we are at the core, the VAE architecture. The input image X goes into the encoder, but instead of outputting a single latent point, the encoder outputs the parameters of a distribution Q phi of z given X, a mean mu, and a standard deviation sigma. Then we sample a latent vector z and feed it into the decoder to reconstruct. x hat, which is modeled as p theta of x given z, but sampling looks non-differentiable, so how do we backprop? That's exactly why we use the reparameterization trick. Instead of sampling directly from the normal distribution of mu and sigma square, we sample epsilon follows the normal distribution and set z is equal to mu plus sigma times epsilon. Now mu and sigma stay inside the computation graph, so gradients flow cleanly back through the encoder. That's the key that makes VAEs channelable. So we've solved the chaining mechanics. We can sample a latent vector z and still backprop through the encoder. Now the next question is, what distribution are we actually trying to learn inside the encoder? Ideally, we want the true posterior p of z given x. That means given an observed input x, where latent z values are truly possible behind it. According to VAEs rule, p of z given x equals p of x given z times p of z divided by p of x. The good news is the numerator is friendly. P of x given z is exactly what our decoder is modeling. The P of z is the prior we choose, usually a standard normal, but the denominator P of x is the troublemaker. This term is called the evidence. To compute P of x, we have to integrate P of x given z times P of z over all possible values of z. And this why this becomes intractable. Once z is high dimensional, integrating over every possible z is basically impossible, not just analytically, but even numerically. So here is the key takeaway of this slide. We cannot directly compute the true posterior P of z given x. Instead, we introduce a practical workaround. We approximate the true posterior using the neural network. That approximation is our encoder distribution Q phi of z given x, and that's the bridge to what comes next. Once we commit to Q phi as an approximation, we can turn the whole problem into something we can actually optimize. So we've said we cannot compute the true posterior P of z given x exactly because the evident term requires an impossible integral. What we do instead is something very standard in variational inference. We stop trying to optimize the exact quantity and we optimize a quantity that we can compute and differentiate. The quantity is called the evidence lower bound, or ELBO. The key statement on this slide is log p of x is greater than or equal to ELBO. So if we maximize ELBO, we are indirectly pushing up log p of x. Even though we can't compute it directly, now here's what ELBO looks like in words. ELBO has two parts. One part is negative KLO divergence between Q phi of z given x and P of z. This is the regularization pressure. It forces the encoder distribution to stay close to the prior, usually a standard normal. In plain language, it keeps the latent space organized and smooth, so we don't get weird, isolated pockets. The other part is the expected value of log p theta of x given z. This is the reconstruction pressure. It rewards the decoder when the sampled latent z can recreate the original input x accurately. So the story is very clean. One turn says keep the latent space will be halved, and the other turn says make the reconstruction fastful. Maximizing ELBO is how a VAE learns a latent space that is both sampleable and useful. Now let's make the approximation idea concrete. We already decided we will not compute the true posterior P of z given x. Instead, we build an approximate posterior Q phi of z given x, and we choose a family of distributions that is simple enough to work with. The most common choice, and the one shown here, is to assume Q phi of z given x is a Gaussian distribution with mean mu and variance sigma squared. So the encoder's job becomes very specific. Given x, predict the parameters of late Gaussian. You can literally see it in a diagram. The encoder processes the input through the hidden layers, then splits into two heads. One head predicts the mean mu, the other head predicts the variance sigma square, or equivalently the standard deviation sigma. Once we have mu and sigma, the approximation is fully defined, and then everything clicks. We can sample z from the Gaussian, feed z into the decoder, and use the ELBO terms to update both networks. So variational here really means we replace an impossible posterior with a learnable parameterized distribution that we can chain end-to-end. At this point, we can summarize the whole VAE in one clean loop. We start with an input x and pass it through the encoder. Instead of outputting a single code, the encoder outputs two numbers, a mean mu and a standard deviation sigma. Those numbers define a Gaussian distribution for Q phi of z given x. Next, we sample a latent vector using a reparameterization check. In words, z equals mu plus sigma times epsilon, where epsilon is standard normal noise. That's what keeps sampling compatible with backprop. Then we decode, we feed z into decoder, and decoder outputs a reconstruction x height. Finally, we optimize a combined objective with two forces. The reconstruction loss pushes x height to match x. The K-low loss pushes the encoder distribution toward the standard normal prior, so latent space stay structured. And that's the full VAE pipeline. Encode a distribution, sample through noise, decode a reconstruction, and chain with reconstruction plus K-low. That's